Tetsuya Hashimoto from the work, yes, from National Chongqing University. We'll be talking about FRB with LOT and FAST. Please take it away.
Okay.
And let's welcome Professor Hashimoto.
Okay, it works. Okay, thank you very much for this opportunity. I'm Tetsuya Hashimoto from National Chongqing University. So today I'm going to talk about simultaneous observations of hyperactive repeating fast radio bursts using FAST in China and LOT in Taiwan. So on behalf of this LOT FAST collaboration team, I also appreciate Shotaro for giving me this slide for today. So let me get started today. So this is my talk plan, which includes the motivation and the strategy of my observation, and then I will discuss my result and discussion, and then I will conclude at the end of my talk. Okay, let me get started with motivation first. As already outlined by Chimpin, so I skip details, but fast radio burst, FRBs, are mysterious, coherent radio emission. Mostly they are coming from extragalactic universe. And then I just wanted to emphasize that in this TPS meeting, in addition to Chimpin and then Jija, there are several presentations about the fast radio burst, including Vignesh and Shotaro, Tomoki, Jonjin, Mohan, and Jiachen. So if you are interested in fast radio burst, please visit their presentations. Okay, and then one of the unique characteristics of fast radio burst is coherent radio emission. And actually pulsars, they are famous for coherent radio emission in astronomy. It's been 60 years since the first discovery of pulsars. If you plot pulsars in this diagram, which is luminosity as a function of duration of different astrophysical sources in the universe, so they are located at here. Then if you overplot fast radio bursts, so they are here. So fast radio bursts, they are roughly speaking, so more than 10 orders of magnitude brighter than pulsars. And the point here is that even for pulsars, it's been controversial. I mean, radiation mechanisms of pulsars has been controversial for about 60 years. So therefore, it's easy to imagine that it's more challenging to understand mechanism of radiation mechanism of fast radio bursts. So therefore, understanding this radiation mechanism is very important in astronomy. Maybe it's not only because of astrophysical reason, but this is a physics point of view. It's very interesting to understand. If you want to know more about the radiation mechanism, please visit Shotaro and Tomoki's talk in this conference. Okay. And then, so far, there are two major different models of radiation mechanisms of fast radio burst. So as Chimpin mentioned, one is this pulsar-like model. So in this model, FRBs are supposed to happen nearby the source of a progenitor source here, maybe inside magnetosphere. And then another model is gamma ray burst-like model. So in this model, FRBs are supposed to happen far away from the progenitor. So if flare happens from this progenitor, this flare can interact with material surrounding this progenitor, and then shock may happen, then this shock can generate the fast radio burst. This happens far away from a progenitor. The problem is we don't know which is the case for fast radio burst. We really want to understand which is the case for fast radio burst, but we don't know. This is because if you look at only radio data, so basically these two major models, both of them can reproduce the characteristic features of fast radio burst, let's say including the coherent radio emission, very bright, and also time scale millisecond. All of these kind of things can be reproduced by both of these two models. Therefore, just by looking at the radio data, it's hard to differentiate between these two models. This is a problem. So this is also a reason why Chimpin is talking about X-ray. Therefore, solutions should be in multi-wavelength data. And I want to emphasize that optical wavelength is really important because optical includes a big question in astronomy. So let me explain. If you look at any type of extragalactic sources, extragalactic transients, all of them has optical counterparts. So the next key question is optical counterpart of first radio burst. And then this optical counterpart of first radio burst is really useful to understand the radiation mechanism of first radio burst. This is because the difference between different models shows up in optical. So this is the predicted optical to radio emission of first radio burst for different physical models, including pulsar-like model and then GRB-like models with different colors here. And then basically these three include inverse Compton process in this model, so therefore they show the very bright optical counterpart here. Anyway, it's very important to constrain these radiation mechanisms. It's very important to conduct the simultaneous observations between radio and optical. And also it's important to have fast optical camera which can achieve millisecond time resolution, which is comparable to the time scale of first radio burst. Then to do so, we made our observations. Let me explain our strategy and observations. So first of all, we target the famous repeating first radio burst, which is called hyperactive repeating FRB source. This is hyperactive because more than 12,000 FRBs were detected from this FRB source. And also this FRB source was localized at a galaxy at distance of redshift 0.13. So we already know the position of this FRB. So this is the best target for our purpose because there are so many FRBs happening from this source. So therefore, we can secure the FRB detection during our simultaneous observations between radio and optical. Okay. And then to do so, we are collaborating people in the first observatory. First is the largest single dish radio telescope in the world in China. And then due to the superb sensitivity of first, actually they can secure the detection of first radio burst during the simultaneous observations. From Taiwan side, we really need a flexible optical telescope which has a TOO capability. TOO means target of opportunity. This is because there is an active activity of FRBs. So we really need to catch the timely activity of repeating FRBs for this case. To do so, we need a flexible optical telescope which can do this TOO observation. We really want to trigger observations at proper time. Then fortunately in Taiwan, we have this Luling Observatory, 1 meter optical telescope. And also thanks to Zhou Jun at NTHU, he has a CMOS camera. So we are able to attach a CMOS camera to this telescope to achieve millisecond time resolution in optical. Then we use these two telescopes. We are collaborating with first people to use these two telescopes to conduct the simultaneous observations. Then actually, overlapping time between these two telescopes was in total 40 minutes for this time. And then let me emphasize, actually I really appreciate, we appreciate this LOT staff and also this opportunity, TEEP and IIPP opportunities organized by NSTC and MOE in Taiwan, because this project gave us a very good opportunity especially for students to gain some research experience. But this is not only for research, but also educational purpose. This is very important. So therefore, I really appreciate LOT and then this programs. Thank you very much. And then let me explain my results. Okay, I have enough time. Fortunately, during this 40 minutes simultaneous observations between first and then Luling Observatory, more than 78 first radio bursts were detected. And then here I show some examples, 5 examples of FRB detections. This is frequency in y-axis as a function of time, observed time. And then you can see bright these spots here, right? So they are clear detections of fast radio bursts. I also show the typical time scale of optical observation, which has actually 17 milliseconds time resolution. This means in optical, we take many snapshots or in optical image, and each snapshot has 17 milliseconds exposure time. So one frame corresponds to 17 milliseconds. So in this case, so we can search for the optical frame which covers the arrival time of individual detection of fast radio burst. And then as a result, we found that out of 78, 64 FRBs were actually covered by our optical frames using Lurin CMOS camera. And then we can go to individual images of optical data. Unfortunately, we didn't find a clear detection. We didn't find a clear point source in the individual optical frame. However, thanks to these 64 detections covered by optical observations, we can stack the optical image, 64 frames. And then this can provide us with a factor 8 gain in the sensitivity in the optical data. And then again, we didn't see any clear detection at the position of FRB in the stacked image as shown here. But this 64 images or factor 8 gain gives us a very strong constraint or upper limit on optical to radio ratio of fast radio burst, which is shown in this diagram. So this is again 5 sigma upper limit on optical to radio or ratio of fast radio burst for different FRB sources here. Our data point is shown by red star here. I would say our upper limit is stronger than previous another upper limit given by another 1-meter optical telescope in Japan. This is basically because we detected many FRBs within our observations. I would also say our constraint is comparable to the one placed by 8-meter optical telescope. This is again thanks to the many FRB detections. The most important thing is our upper limit is below this horizontal red dashed line here. This means our upper limit excludes the brightest case of the pulsar-like scenarios of FRB models. Okay, let me conclude here. Optical counterpart is very important. So we exclude the brightest case of FRB models of optical counterparts. Okay, I stop here. So thank you very much.
Can you go back to the FRB slide?
Sure.
Yeah, because we in general, like FRB have a lag in low frequency band, but this one seems to have a lag in high frequency band. Why?
Could you say
time lag in low frequency. But
time
this figure seems to have a lag in high frequency.
No, I think this is after the dispersion. Then you may see tilt here. This tilt is probably not the perfect correction for the dispersion, maybe. This happens because, say, this can be intrinsic morphology of FRB individual or can be inaccurate correction for the dispersion measure. But for this is repeating FRB, so therefore they really use, say, I think for this case, they use a representative dispersion measure for this source. But dispersion measure can slightly change, right, burst by burst. Okay. So therefore, this may adjust, actually.
Thank you.
Yeah, thank you very much.
Any other questions from audience? Wolfgang first.
Okay, so my question is not in this field, so my question is very naive. So then,
Wolfgang, could you?
Because this your case is the brightest. So do you expect that the normal FRB would, well, then I mean, my question is how is it possible if you want to know like the more normal FRB and using optical, because you expect the optical will be very, very thin, and is it even possible even use our base telescope?
I see. Thank you very much. That's a very important point. Actually, for this observation limitation, we are targeting very special source out of many FRB sources. This is hyperactive. So in that sense, this may be the special target, which cannot be, it may not be able to apply the same thing to the general population of FRB. That's one thing. I think that makes sense. Yes. Then if we want to investigate the general population, I think one thing is we can really focus on nearby FRBs. If it's nearby, then everything becomes easy to observe, including radio and optical. So then I can advertise in Taiwan, we are building the burst telescope, which will find a very nearby first radio burst. Then I hope once burst starts their size operation, then maybe we can do better using burst samples. Thank you very much.
Final question from Mr. The last one.
Thanks for a pretty nice talk. I'm curious about why you're so confident there is the optical source overlay with the FRB.
I'm sorry. I'm sorry. In that sense, I'm not that confident. Yes, because there was no detection of optical counterpart so far, but maybe motivated by this theoretical prediction, theory expects non-zero emission in optical. So therefore, naively speaking, we may expect from this theoretical point of view. But I think you are right. It's possible that there is no optical counterpart. But in that case, it's still, I think, constrain some radiation mechanisms, I think. Therefore, it's from observation side, I think it's good. It's important to make sure if they exist or not.
Sure, thank you very much.
All right. With that, let's thank Professor